Hello there, and welcome to the Sleepy Science Hour. Tonight, we are going to talk about something that has never truly been witnessed, not from beginning to end, not by any human eye, and not by any instrument we have ever built. It is something that takes longer than civilizations, longer than our entire species has walked this earth. It is something that happens in the darkest, coldest, most silent corners of the galaxy, in places so remote and so still that even light struggles to pass through them. And yet, without it, none of us would be here. No planet, no ocean, no sleeping body lying in the warmth of a bed on a quiet night. Tonight, we are going to follow the slow, patient, almost impossibly gentle birth of a star. And if you enjoy spending your nights this way, drifting off to the quiet wonders of the universe, please consider subscribing to the channel or leaving a comment to let us know you are here. But first, before we go anywhere at all, take a moment with me. Let your body settle into whatever surface is holding you. Feel the weight of your limbs go soft. Let your shoulders drop just a little. Let your jaw unclench. Let the sounds of the day, the conversations, the notifications, the small worries and unfinished thoughts, let them begin to drift to the edges, like clouds moving slowly toward the horizon. You do not need to hold on to anything tonight. The universe will do all the work. You only need to listen. Let your eyes grow heavy if they want to. Let your breathing slow. Let the room around you grow quiet and kind. We are going somewhere very far away and very, very still. Let's begin. There is more nothing in the universe than anything else. We talk about space as though it is full. We imagine stars scattered generously across the dark, like salt spilled on a black tablecloth. And in some ways, that image is not wrong. There are more stars in the observable universe than there are grains of sand on every beach and desert on Earth. The number is almost beyond holding in the mind. And yet, if you could stand inside any given region of space and look around, what you would find, overwhelmingly, is emptiness. Between the stars, there is distance so vast that the light traveling across it would take years, centuries, millions of years. The stars, for all their number, are islands. Small, bright, isolated islands in an ocean of almost nothing. We tend to think of that almost nothing as truly nothing, as pure vacuum, as the absence of everything. But the deeper truth is stranger and quieter than that. The space between stars is not empty. It never quite is. Scattered through the dark, thinly and unevenly, are the ingredients for everything that has ever existed or ever will. Hydrogen atoms, helium, traces of carbon, oxygen, nitrogen, and iron. Fine grains of dust, each one smaller than the period at the end of this sentence. Magnetic fields threading silently through the dark like invisible rivers. And cold. A cold so profound it approaches, but never quite reaches, the lowest temperature the universe allows. This is the interstellar medium, the medium between the stars. And it is not a place of nothing. It is a place of almost nothing, which is a very different thing. Because almost nothing, given enough time, given the right conditions, given the slow and patient pull of gravity, almost nothing can become a sun. That is what we are going to watch tonight. Not quickly, never quickly. We are going to follow the universe doing what it does best, which is waiting and whispering and slowly, gently, inexorably becoming. Somewhere in a galaxy, perhaps this one, there is a region of space where the interstellar medium has thickened slightly, where gas and dust have drifted together over millions of years, drawn by the faintest tug of mutual gravity, pooling like mist settling into a valley. These regions have a name. We call them molecular clouds, because inside them, where the density is just high enough to offer shelter from the radiation of nearby stars, individual atoms have found each other and bonded together into simple molecules. hydrogen paired with hydrogen, carbon joined to oxygen, water in frozen form, ammonia, methanol. Even in the depths of some clouds, simple organic molecules whose names would surprise you if you heard them in this context. These clouds are not small. They are, in fact, among the largest structures formed by ordinary matter in the universe. A typical molecular cloud might stretch across 50 to 200 light-years. Some of them, the great complexes that astronomers call giant molecular clouds, span thousands of light-years. The Orion Molecular Cloud, which you might have encountered if you have ever looked up at the winter sky and noticed the 3 bright stars of Orion's belt, extends across roughly 400 light-years of space. It contains enough gas and dust to make hundreds of thousands of stars the size of our sun. And yet, standing on Earth and looking toward it, you would see almost nothing. The visible light from distant stars behind it is absorbed by the cloud's dust. It looks like absence, like a gap in the stars. Ancient astronomers sometimes thought these dark patches were holes in the sky, windows into the void beyond the stars. They were not wrong that something unusual was happening there, but they were beautifully, wonderfully wrong about what it was. The darkness was not absence. The darkness was potential. It takes a different kind of eye to see a molecular cloud for what it is. Radio waves pass through the dust that blocks visible light, and when astronomers began mapping the sky in radio frequencies in the mid-20th century, the dark patches lit up. Not with light, but with the precise, unmistakable radio signatures of molecules, hydrogen, carbon monoxide, ammonia, all broadcasting their presence in wavelengths far too long to see but perfectly suited to be heard. And what those radio signals told us was staggering. The galaxy is threaded with these vast, dark reservoirs of gas and dust. They are not rare, they are everywhere, and they are the birthplaces of every star you have ever seen. Every single one. The oldest stars in the night sky, the ones that formed when the universe was barely 1 billion years old, began as gas and dust in a molecular cloud. The sun you felt on your skin today began as gas and dust in a molecular cloud about 4.5 billion years ago. And somewhere, right now, in a cloud you cannot see because it absorbs the light passing through it, a star is beginning its slow, slow journey toward existence. The first thing you need to understand about a molecular cloud, the thing that makes its story so different from what you might expect, is how extraordinarily cold it is. We are not talking about the cold of a winter night. We are not even talking about the cold of Antarctica, where temperatures can fall to minus 90 degrees Celsius. We are talking about temperatures that hover between 10 and 30 Kelvin. Kelvin is a temperature scale that begins at absolute zero, the point at which all molecular motion ceases, the coldest possible state of matter. 10 Kelvin is 10 degrees above that. It is about minus 263 degrees Celsius. It is, in every meaningful sense, as cold as things get while still technically having a temperature at all. At those temperatures, the molecules in the cloud barely move. They drift. They wander. They bump into each other only rarely. If you placed your hand into such a cloud, which is impossible, but let us imagine it anyway, you would not feel it the way you feel ordinary cold. The cloud is too thin, the molecules too sparse, for much heat to be drawn from your skin in any ordinary sense. It is more like the cold of deep space itself. Quiet, vast, profound. And it is precisely this cold that makes star formation possible. If a molecular cloud were warm, the gas inside it would have too much energy to fall together. Heat is motion. Warm gas molecules move fast, bouncing and pushing outward, resisting compression. A warm cloud wants to expand, to spread out, to fill any available space. It cannot collapse under its own gravity because its own internal energy keeps pushing it apart. But a cold cloud is different. Cold means slow. Cold means still. Cold means the gas has very little energy pushing outward. And so, When gravity pulls inward, there is much less resistance. Not no resistance, we will come to that, but less. And that small advantage, that delicate imbalance between gravity pulling in and heat pushing out, is what begins the whole impossibly long process. Think of it like this. Imagine a crowd of people standing on a flat plane, all walking slowly and randomly in different directions. Now imagine the plane has a very slight, almost imperceptible slope, just a degree or two, barely enough to notice. At first, the random movement of the crowd overwhelms the slope entirely. People wander in every direction. But over time, a very long time, slightly more people drift downhill than uphill. Gradually, almost without anyone intending it, the crowd begins to concentrate at the bottom of the slope. Not because anyone chose to go there, but because the gentle, persistent nudge of the slope was always there, slowly winning. That slight slope is gravity. The random movement of the crowd is the thermal motion of the gas molecules. And what happens at the bottom of the slope, the slow, unintended gathering, is the first whisper of a star. This gathering does not happen quickly. This is perhaps the most important thing to understand about the birth of a star. It is not an event. It is not a moment. It is a process of almost unthinkable slowness, stretched across timescales that make human history look like a single heartbeat. A typical star-forming cloud might take anywhere from 10 to 100 million years to produce its first stars. 10 million years. The dinosaurs first appeared on Earth roughly 230 million years ago. If a cloud had begun forming stars at exactly that moment, those stars might only now be approaching the end of their earliest, clumsiest phase of formation. The cloud would still be, by any measure, young. And this slowness is not a failure of efficiency. It is not the universe being clumsy or delayed. It is a deep consequence of the physics involved, of the competing forces pulling in different directions, of the fact that gravity, for all its reputation as the dominant force of the cosmos, is extraordinarily weak when applied to thin gas spread across hundreds of light years. We tend to think of gravity as powerful, and on human scales, on planetary scales, it is. You feel its pull every moment of your life. It holds the atmosphere around the Earth, keeps the moon in its orbit. It holds the sun together, but gravity's strength drops off with distance. And in a molecular cloud, where the mass is spread incredibly thinly across an enormous volume, the gravitational pull at any given point is almost imperceptibly small. A single hydrogen molecule in the middle of a molecular cloud feels the gravitational attraction of the rest of the cloud like you might feel the pull of a single grain of sand on the other side of a football field. It is there. It is real. But it is almost nothing. And yet almost nothing multiplied by millions of years is enough. There is a number in astrophysics called the freefall time. It represents how long it would take for a cloud of gas to collapse under its own gravity if nothing were resisting it. No heat, no magnetic fields, no turbulence, just pure, unimpeded gravitational collapse. For a typical molecular cloud, the freefall time is somewhere between a few million and a few tens of millions of years, which sounds long by human standards. But in cosmic terms, it is actually quite short. The universe is nearly 14 billion years old. A few million years is, relatively speaking, not much more than a moment. And yet stars do not form on the freefall timescale. They take much, much longer. Why? Because the cloud is not simply sitting still, waiting to be squeezed. It is alive in its own cold, slow way, with motion and resistance and forces that push back against the inward pull of gravity with remarkable stubbornness. The first of these forces is turbulence. When we hear the word turbulence, we might think of the stomach-lurching motion of an airplane passing through choppy air, or the churning surface of a river around a rock. Turbulence, in everyday life, is something we experience as disorder, as roughness, as unpredictability. things. But it is also something else. It is a support structure, a scaffold. Molecular clouds are not still. Despite their extraordinary cold, they are threaded with internal motions. Vast, slow waves of compression and rarefaction moving through the gas, regions denser here and thinner there, currents of materials sweeping this way and that across distances of many light years. These motions are driven by many things. The energy injected by nearby massive stars before they explode, the shock waves from supernovae rattling through the interstellar medium, the gravitational interactions between the cloud and the rest of the galaxy. And these turbulent motions provide pressure. Not the pressure of heat, not the rapid, random jostling of warm molecules, but something more organized, more structured. The turbulence creates a kind of scaffolding inside the cloud, regions of extra pressure that hold the gas up against gravity, preventing it from all falling inward at once. Without turbulence, a molecular cloud would collapse entirely on its freefall timescale, producing a brief, violent burst of star formation and then going quiet. With turbulence, the collapse is slower, more irregular, more fragmented. Some regions collapse while others are held up. Some pockets of dense gas fall together while turbulence churns and stirs and redistributes matter elsewhere. The result is not one star, but many, formed gradually over millions of years in different corners of the cloud, each one the child of a local pocket of calm amid the larger storm. Turbulence is why our galaxy has been forming stars steadily for billions of years, rather than in a single cataclysmic rush early on. It is the reason the Milky Way is still alive with stellar birth today. Turbulence is not the enemy of star formation. It is its pacing mechanism, its regulator, its metronome. The second force that resists gravitational collapse is one that surprises many people when they first encounter it. It is not heat. It is not turbulence. It is magnetism. Molecular clouds are threaded with magnetic fields, not strong ones by the standards of a bar magnet or an MRI machine. The magnetic fields in a molecular cloud are astonishingly weak, measured in microgauss, millionths of the already small unit of magnetic field strength. By the standards of anything you might encounter in daily life, they are essentially undetectable. And yet, they matter enormously. The reason is that the gas in a molecular cloud, while mostly neutral, electrically balanced, with equal numbers of positive and negative charges, is never perfectly neutral. There are always a few ions threading through it, atoms or molecules that have lost or gained an electron and therefore carry a net electrical charge. These ions are tied to the magnetic field. They cannot cross the field lines freely. They can only slide along them like beads on a wire. And here is the crucial thing. When the ions are tied to the magnetic field, and the neutral gas is loosely coupled to the ions through collisions, the magnetic field effectively holds the whole cloud together, threading through it like a rigid skeleton inside a body of soft tissue. When gravity tries to pull the cloud together perpendicular to the field lines, it has to drag those field lines along with it, and compressed magnetic fields push back. They resist being squeezed together. They create a magnetic pressure that opposes the gravitational compression. The result is that a cloud threaded by a strong magnetic field can sit, almost indefinitely, in a state of near balance between gravity and magnetic support. It does not collapse quickly. It barely seems to collapse at all on human timescales. But there is a way out, a slow, patient, almost invisible process called ambipolar diffusion. The neutral atoms in the cloud, the vast majority of the material, are not tied to the magnetic field. They only feel it indirectly through their occasional collisions with the ions. And so, over time, the neutral atoms can drift very slowly relative to the ions and the magnetic field. They slip through the invisible magnetic scaffolding like sand through a loose net. They do not do this quickly. On the scale of individual atoms, the drift is imperceptibly slow. But over millions of years, the neutral gas gradually concentrates toward the densest central regions of the cloud, where gravity is strongest, leaving the magnetic field spread more thinly behind. Ambipolar diffusion is the universe's way of slowly, patiently allowing gravity to win. It takes somewhere between 10 and 100 times the freefall time for ambipolar diffusion to work, which means that in magnetically supported regions, star formation is drawn out over timescales of hundreds of millions of years. Patient, slow, almost imperceptible progress toward the moment when the gas finally, quietly, tips over the edge and begins to fall. There is something calming about this if you let yourself feel it. The universe is in no hurry. It has learned through the long logic of physics that the best way to build something lasting is to go slowly, to let gravity work not in one violent rush, but in a quiet, persistent accumulation that takes as long as it takes. There is a threshold at the heart of star formation, tipping point, and it has a name, the Jeans instability. In the late 19th century, a British physicist named James Jeans was thinking about exactly this problem. What conditions are needed for a cloud of gas to collapse under its own gravity? He worked out the mathematics and arrived at a beautiful, simple criterion. A cloud of gas will collapse if its gravitational energy, the energy of all its matter pulling itself together, exceeds its thermal energy, the energy of its molecules trying to push outward. When gravity wins that contest, even slightly, collapse becomes inevitable. The dividing line between stability and collapse is described by what we now call the Jeans mass and the Jeans length. The Jeans mass is the minimum mass a cloud must have at a given temperature and density in order to be unstable to gravitational collapse. If the cloud's mass exceeds the Jeans mass, gravity wins. If it falls short, thermal pressure holds. And here is what is elegant about it. The Jeans mass depends strongly on temperature. Cold clouds have a lower Jeans mass than warm ones, which means that in the cold interior of a molecular cloud, even relatively small clumps of gas, clumps that might be mere fractions of the cloud's total mass, can become individually unstable. This is why molecular clouds do not form a single star. They form many. As a cloud contracts or as turbulence compresses local regions to higher densities, pockets of gas can exceed the local Jeans mass and begin to collapse on their own, independently of the larger cloud around them. These collapsing pockets, called prestellar cores, because they are the precursors of individual stars or small groups of stars, are each following the same general script as the larger cloud, but at a smaller scale and on a somewhat shorter time scale. A molecular cloud, then, is not a single collapsing entity. It is more like a loaf of dough, riddled with pockets of denser material, some rising, some not yet ready, all on their own timeline. And as the dough of the cloud slowly contracts and thickens over millions of years, more and more of those pockets cross the Jeans threshold and begin their own private journey towards stellar existence. This is called fragmentation, and it is why stars come in groups, in clusters, in associations of dozens or hundreds or thousands of siblings, all born from the same original cloud, all beginning their lives in the same neighborhood of the galaxy, before slowly drifting apart over the hundreds of millions of years that follow. You have heard of the Pleiades, perhaps, the Seven Sisters, that loose, beautiful cluster of blue-white stars visible to the naked eye in winter. They are siblings in exactly this sense. They formed together from the same molecular cloud, roughly 100 million years ago. They are still relatively close together in space, still moving together through the galaxy. But over the next few 100 million years, they will slowly drift apart, scattered by gravitational interactions with other stars and clouds, until they are indistinguishable from the background stars around them. Our own sun may have had siblings once, stars formed from the same cloud in the same cluster, but the cluster has long since dissolved, scattered across the galaxy over 4.5 billion years. Those sibling stars are out there somewhere, moving through the Milky Way, older now and not recognizably related in any way we have yet been able to determine. We share an origin with stars we cannot name, spread across distances we cannot currently bridge. There is something in that which feels, in the dark, like a very old kind of loneliness, and also, somehow, like belonging. When a prestellar core forms, when that pocket of dense, cold gas in a molecular cloud tips past the gene's threshold and begins to collapse, the first phase of its journey is almost entirely invisible. Not invisible in a poetic sense, literally invisible to any telescope that observes ordinary visible light. The gas and dust of the collapsing core are dense enough to block light from within and without. No photons of visible light escape. No glow, no shimmer. The core collapses in a kind of perfect darkness, folding inward on itself in silence over a period of hundreds of thousands of years. The only way to detect a prestellar core in this earliest phase is through the cold glow of the dust itself. Not visible light, but far infrared and submillimeter radiation, the faint warmth of particles that are a few degrees above absolute zero. Even this is barely detectable with modern instruments. We can see these cores with telescopes like the Herschel Space Observatory and the James Webb Space Telescope's infrared instruments, but only barely. Only as the faintest, coldest whispers of structure in an already cold and dark region of space. And what those observations tell us is both simple and extraordinary. The core is collapsing fastest at its center. The outer regions are still falling inward, but the inner regions are denser and therefore collapsing faster. The result is an ever-sharpening concentration of mass at the center, a growing knot of density that will eventually, if everything proceeds as it should, become the nucleus of a new star. There is a moment in this collapse, a specific critical moment, when the gas at the center becomes dense enough to be opaque to its own radiation. Up to that point, the energy released by the gas as it falls inward and compresses can escape outward as infrared radiation. The collapse stays cold. The energy escapes before it can build up and heat the gas significantly. But when the central density crosses a certain threshold, somewhere around 10 to the 13th hydrogen molecules per cubic centimeter, an almost incomprehensibly dense number, the gas becomes opaque. The radiation is trapped. And now, as the gas continues to fall inward and release gravitational energy, that energy has nowhere to go. The trapped energy heats the gas. And as the gas heats, it begins to push back. The pressure rises. The rate of collapse slows. The central region reaches a kind of fragile, temporary equilibrium. Not a star yet, not even close, but a warm, dense, slowly growing object that we call the first hydrostatic core. It is about the size of a few astronomical units, a few times the distance from the Earth to the Sun. It is warm, perhaps 100 to 1,000 Kelvin at its center. It is still surrounded by a vast envelope of infalling gas and dust, and it is just barely holding itself up against the continued inward pressure of the collapse. It will not hold long. As more material falls onto the first hydrostatic core, its temperature rises further. And when the temperature at its very center reaches about 2000 Kelvin, something remarkable happens. The hydrogen molecules, which up to this point have been the fundamental building blocks of the gas, begin to break apart. The molecules dissociate into individual atoms. This process absorbs energy. It takes energy to break apart a molecule, and as the core's thermal energy is suddenly consumed in this dissociation, the pressure drops. The temporary equilibrium shatters. The core collapses again, a second, faster collapse, much smaller in scale than the first. The inner region falls inward in a matter of years, compressing into something truly dense, something truly new. This is the second collapse, and from it emerges the protostar. Protostar is not yet a star, not quite. It has not yet ignited the thermonuclear fusion reactions that will eventually define it, that will power it for millions or billions of years. But it is, for the first time in this long journey, an object that radiates energy, its own energy, produced by the compression of infalling gas, with something like genuine brightness. A protostar at this stage is roughly the size of a few solar radii, hot at its center, perhaps tens of thousands of Kelvin, surrounded still by its thick cocoon of dust and gas, which absorbs its light and re-radiates it at infrared wavelengths. To any visible light telescope, it is still invisible, still hidden inside the dark cloud. But in the infrared, it glows, faintly, unevenly, embedded in the heart of a warm region that infrared telescopes can detect as a bright knot of warmth in an otherwise cold cloud. We call these embedded protostars class 0 sources in the astronomical classification system. Class 0 because they are at the very beginning, before anything that we would recognize as stellar has truly begun. And the defining feature of a class 0 source, the thing that marks it as genuine, is not just its warmth but its appetite. It is accreting, taking in mass from the surrounding infalling envelope, growing, slowly getting heavier, hotter, denser. A protostar at this stage might have a mass only 1/10 or 1/100th of what the final star will have. It is, in every sense, an infant, and like many infants, it is not quiet. One of the most surprising discoveries of modern star formation science, something that no one predicted before it was observed, and that took years to fully explain, is that very young protostars, embedded in their dark cocoons, produce powerful jets. Not trickles, not gentle outflows, jets. Narrow, collimated beams of gas, moving at hundreds of kilometers per second, launched from the immediate vicinity of the protostar and shooting outward along the axis of rotation, punching through the surrounding envelope and into the molecular cloud beyond. These jets can extend for light years. They slam into the surrounding gas and create beautiful, ghostly structures called Herbig-Haro objects, named for the two astronomers George Herbig and Guillermo Haro, who first cataloged them in the 1950s, though at the time no one understood what they were. They appear as glowing arcs and knots of gas, lit up by the shock wave of the jet slamming into slower-moving material, painting the dark clouds with curves and filaments of green, red, and blue light. The Hubble Space Telescope has photographed Herbig-Haro objects in extraordinary detail, and they are among the most beautiful things in the observable universe. They look like the trails left by something that has just passed, like the wake of a boat on dark water, or the brushstroke of some enormous, invisible hand. But why do protostars produce jets? The answer lies in the geometry of the collapse. When a prestellar core collapses, it is not falling together uniformly from all directions. The core is rotating, however slowly, and as it collapses and its radius shrinks, its rotation speeds up, just as a spinning ice skater draws in their arms and spins faster. The conservation of angular momentum, the same principle that keeps a top spinning and keeps the planets orbiting the sun, demands that as the collapsing gas gets smaller, it must spin faster. But a spinning collapse cannot simply fall straight inward. The spinning gas has centrifugal tendency. It tends to fly outward along the equator, perpendicular to the rotation axis. So while the gas at the poles of the collapsing core can fall straight in toward the protostar, the gas at the equator spreads out into a flat, rotating disk. This is the accretion disk, the spinning pancake of gas and dust that forms around the young protostar, carrying most of the angular momentum of the original cloud. The disk feeds material onto the protostar slowly, spiraling inward like water draining down a drain in slow motion, and through a process involving magnetic fields threading through the disk, a process that is still not fully understood in all its details. Some fraction of the infalling material is flung upward and downward along the rotation axis at tremendous speed. These are the jets. They are, in a sense, the protostar's way of dealing with a problem. To grow, to add mass, the protostar needs to accrete material from the disk. But accreting material also means accreting angular momentum, which would make the protostar spin faster and faster until it flew apart. The jets carry away the excess angular momentum safety valve releasing pressure from a building system. By launching mass along its rotation axis, the protostar can continue to grow without spinning out of control. It is a beautiful, if violent, solution to a fundamental problem of physics. And the violence of it, the jets traveling at hundreds of kilometers per second, punching through light years of cloud, is perhaps the most dramatic thing happening anywhere in the neighborhood of a young star. Yet it is happening in the dark, hidden behind a wall of dust, known to us only through the glowing testimony of the Herbig-Haro objects the jets leave behind. For hundreds of thousands of years, the protostar continues to grow. Material falls from the surrounding envelope onto the disk, and from the disk onto the protostar itself. The protostar gets hotter, its luminosity increases, and as the infall of material heats the surrounding envelope and drives the jets further outward, the protostar begins, very slowly, to clear a space around itself. The envelope begins to thin. The dense, dark cocoon that hid the protostar from the universe becomes gradually more tenuous. The jets and the winds blowing off the surface of the protostar push material outward, carving bipolar cavities, two roughly conical cleared regions extending from the poles of the protostar out through the envelope and into the surrounding cloud. These cavities allow some light to escape for the first time, not from the protostar directly, that is still buried, but scattered off the walls of the cavity, emerging sideways in a soft, nebulous glow. From outside the cloud, looking in with the right telescope, you begin to see something. Faint, diffuse brightening, a hint of structure in what was previously pure darkness. The protostar, in this phase, has entered what astronomers call the Class 1 stage. It is still deeply embedded, still actively accreting from its envelope, still surrounded by enough dust to make it invisible to ordinary light telescopes. But it is no longer completely hidden. It is beginning, in the most tentative way, to announce its existence. This phase lasts for somewhere between 100,000 and a few 100,000 years. It is a period of rapid growth and violent activity. The jets continue to blow. The disk continues to feed. The protostar continues to brighten. And then, gradually, the envelope exhausts itself. The material that has been raining down on the protostar for hundreds of thousands of years is mostly gone now, accreted onto the star or the disk, or blown away by winds and jets. The once thick cocoon has dissolved into a tenuous haze. And for the first time, for the absolute first time in the entire history of this star, light escapes directly from its surface. This is a remarkable moment, but it is also, I should be honest with you, still not quite the moment of stellar birth in the truest sense. The star we see emerging from its cocoon is still not powered by nuclear fusion. It is still living off the energy of gravitational contraction. As the star shrinks, and it is still much larger than it will eventually be, the gravitational energy released by that shrinkage keeps its surface hot and luminous. We call this object, in its newly revealed state, a T Tauri star, if it is roughly sun-like in its eventual mass, or a Herbig Ae/B star if it is more massive. These names come from specific well-studied examples. T Tauri is a young star in the constellation Taurus that first drew astronomers' attention to this class of object in the late 19th century. It was clearly variable, clearly unusual, clearly surrounded by something that made it hard to fit into the standard categories. We know now what that something was: the remnants of the cocoon, the debris of a disk, the chaos of a still-forming solar system. T Tauri stars are extraordinary objects to observe, not beautiful in the serene, regal way of an older sun, but wild in the way of something young and unfinished. They flare. They vary in brightness on timescales of hours to days, as star spots, regions of intense magnetic activity on their surfaces, similar to sunspots but vastly larger and more turbulent, rotate in and out of view. They blast winds far stronger than the solar wind our own sun produces today. They emit powerful X-rays, intense ultraviolet radiation, bursts of energy that would sterilize any planet unfortunate enough to be nearby. And they still have their disks. The protoplanetary disk, the flat, rotating pancake of gas and dust that formed during the collapse, has survived the protostellar phase and persists around the T Tauri star. Now somewhat depleted of the infalling envelope material, but still rich, still massive, still containing everything needed to build a planetary system. In fact, it already is building one. Even while the central star is still finding its feet, still contracting toward the main sequence, the disk around it is quietly beginning the process that will eventually produce planets. Dust grains are sticking together. Pebbles are forming. Small rocks are gathering into larger rocks. The process of planetary formation is beginning its own slow, patient work, overlapping with and running parallel to the final stages of the star's own formation. But that is a story for another night. The T Tauri phase lasts for several million years for a sun-like star. During this time, the star is contracting toward its final size, radiating the energy of that contraction from its surface, slowly getting denser and hotter at its core. And the central temperature is rising toward a very specific number, 10 million Kelvin. That is the threshold for hydrogen fusion, the temperature at which two hydrogen nuclei, two protons, can overcome their mutual electrical repulsion and merge together. When they do, they release energy, not the energy of a chemical reaction, not the modest energy of electrons rearranging themselves around atomic nuclei, but nuclear energy. The energy locked inside the nucleus itself. Energy 4 million times more powerful, weight for weight, than the chemical energy in the finest fuel humanity has ever burned. This is the moment we have been waiting for. Not the formation of the cloud, not the crossing of the gene's threshold, not the protostar or the T Tauri phase or the clearing of the cocoon. Those were all preamble, all preparation, all the slow work of getting the core to the right temperature and pressure. This moment when hydrogen begins to fuse into helium at the very heart of the forming star. This is the true birth. And it is quiet. There is no explosion, no visible flash, no event that any external observer could detect. Deep inside the core, surrounded by hundreds of thousands of kilometers of gas, the first nuclear reactions begin. Protons begin to fuse. Energy begins to flow outward, carried by photons that will take hundreds of thousands of years to reach the surface, bouncing and scattering through the dense interior in a slow, indirect journey. But the effect of those first fusion reactions is immediate and profound in a structural sense. The energy released pushes outward against gravity, providing exactly the support that gravity has been overcome for hundreds of thousands of years. The star stops contracting. The long shrinkage ends. The star settles into a stable configuration, a balance between gravity pulling inward and the pressure of nuclear energy pushing outward that it will maintain with remarkable steadiness for billions of years. This balance has a name. We call it the main sequence. And a star that has reached the main sequence is, by any useful definition, a star. Not a protostar, not a T Tauri object, not a cloud or a core or an almost star. A star, bright, stable, nuclear, real. Our sun is a main sequence star. It has been burning hydrogen in its core for about 4.5 billion years. It has enough hydrogen to continue for another 5 billion years or so. 10 billion years total of steady, stable nuclear burning. 10 billion years of the same essential balance. Gravity inward, fusion pressure outward, light flowing steadily from the surface into space in all directions. From the first thickening of a molecular cloud to the moment of main sequence arrival, the whole process takes, for a sun-like star, somewhere between 10 and 50 million years, which sounds like a long time, but compared to the 10 billion year lifespan that follows, it is nothing. It is less than 1% of the star's total life. It is the gestation period, brief in proportion to the lifetime ahead. More massive stars go through the same general process but faster, far faster. A star 10 times more massive than the Sun can reach the main sequence in as little as 100,000 years. Its core is so dense and hot that fusion ignites almost before the collapse is fully complete, before the cocoon has even begun to thin. Massive stars are the impetuous ones, the impatient ones. They race through their formation, and they race through their lives. A star 10 times the mass of the Sun might live only 10 million years before ending in a catastrophic supernova explosion. A Sun-like star lives 10 billion. The more massive the star, the shorter and more violent its life. There is something almost philosophically satisfying about that. The ones that burn brightest burn shortest. The quiet, modest, middleweight stars like our Sun plod along for billions of years, steady and reliable and easy to overlook. The giants blaze and die young, seeding the galaxy with the heavy elements forged in their cores and scattered in their explosions. Both are necessary. Both play their role in the great cycle. And that cycle, the cycle of gas becoming stars, stars living and dying, and death seeding the gas for the next generation, is one of the most important processes in the history of the universe. The first stars that ever formed in the very early universe were made of almost nothing but hydrogen and helium. Those are the only elements that existed in significant quantity after the Big Bang. The universe was new and nearly pure, and those first stars, enormously massive, burning hot and fast, lived briefly and died violently, seeding the young universe with the first traces of heavier elements. Carbon, oxygen, nitrogen, silicon, iron. The clouds that formed the next generation of stars inherited these traces. And those stars, living and dying in turn, added more heavy elements to the mix, generation after generation. Each stellar death enriching the interstellar medium slightly. Each new cloud of gas containing a slightly higher fraction of elements heavier than helium. Each new generation of stars more complex, more varied, more capable of producing planets with solid surfaces, with liquid water, with the chemistry of life. Our Sun is a third-generation star, at least, perhaps fourth or fifth. We cannot be certain exactly how many generations of stars preceded it. But we know that the atoms in our Sun, the carbon, the oxygen, the iron, the calcium, were forged in stellar cores that lived and died before our Sun was born, before our solar nebula had gathered, before the cloud that would become our Sun had even begun to cross the gene's threshold. And those same atoms, the ones that passed through stellar cores, that were scattered in supernova explosions, that drifted through the interstellar medium and eventually gathered into the cloud that became our solar system. Those atoms are in you right now. The calcium in your bones. It was forged in a stellar core. The iron in your blood. It came from a supernova. The oxygen you breathe in this quiet room. It passed through the heart of a star that died billions of years before you were born. You are not separate from the story of stars. You are the story of stars, continued. You are what a molecular cloud eventually becomes, given enough time and enough generations of stellar life and death. You are, in the most literal and non-metaphorical sense, made of stardust. Carl Sagan said this famously, and it was true when he said it, and it is no less true now, and it will be true long after every person alive today is gone. We are the universe's way of knowing itself, built from the material of dead suns, standing for a brief moment in the light of a living one. There is a star-forming region you can visit with your eyes, if the night is clear and you know where to look. Find the constellation Orion, the great hunter, striding across the winter sky of the northern hemisphere. Follow the 3 bright stars of his belt downward, or in the southern hemisphere upward, and you will come to a faint smudge of light just below the leftmost star of his sword. It does not look like much to the naked eye. A soft blur, almost indefinite, more felt than seen. That is the Orion Nebula, and it is, right now, at this moment, a stellar nursery. Inside that soft smudge, in the infrared wavelengths invisible to your eye, there are hundreds of young stars, protostars still in their cocoons, T-Tauri stars throwing tantrums, Herbig-Haro objects glowing where jets punch into the surrounding gas, protoplanetary disks, silhouetted against the bright background of ionist gas, carrying in them the seeds of worlds that do not yet exist. It is happening right now, the birth of stars, visible, in a sense, from your bedroom window if you know what you are looking at. The Orion Nebula is about 1,400 light-years away, which means the light reaching your eye tonight left that region of space 1,400 years ago. You are looking at Orion as it was in the 6th century AD. The stars you see forming there, or rather, the evidence of their formation that you see, represents the state of the nebula when the Roman Empire had already fallen and the early medieval period was just beginning in Europe. And whatever is happening there now, at this actual moment, you will not see it for another 1,400 years. We are always, in a sense, looking into the past when we look at the sky. The further away something is, the further back in time we see it. The moon as it was a little over a second ago. The sun as it was 8 minutes ago. The nearest star system, Alpha Centauri, as it was a little over 4 years ago. The Andromeda Galaxy, that faint smear of light visible to the naked eye on a dark night, as it was 2.5 million years ago, before Homo sapiens existed. And the most distant objects we can observe with our most powerful telescopes, the faint smudges of the earliest galaxies at the edge of the observable universe. We see them as they were 13 billion years ago, when the universe was less than 1 billion years old, when the first stars were just beginning to form from the first molecular clouds. We are surrounded by history. The sky is a record of time, written in light. There is a particular kind of young star that deserves a moment of attention. A kind of almost star, a near miss, a star that got so close to being a real star and then stopped just short. We call them brown dwarfs. A brown dwarf forms the same way a regular star does, from a collapsing core in a molecular cloud, from a prestellar core crossing the gene's threshold, from a protostar accreting mass and growing. But somewhere in the process, the accretion stops. The cloud runs out of material to provide, or the object's own winds and radiation drive away the surrounding gas before enough mass has accumulated, or the core simply did not start out with enough material to grow into a full-scale star. And the result is an object with a mass somewhere between about 13 and 80 times the mass of Jupiter, the giant planet that is the largest in our solar system. This range of masses sounds large, and it is in planetary terms, but it falls short of the roughly 80 Jupiter masses needed for sustained hydrogen fusion. The core of a brown dwarf gets close to the temperature needed for full hydrogen burning, but not quite close enough. What brown dwarfs can do is burn deuterium. Deuterium is a form of hydrogen whose nucleus contains not just one proton, but a proton and a neutron. It is rare, only about 1 in every 6,000 hydrogen atoms in the universe is deuterium, but it fuses at a lower temperature than ordinary hydrogen. A brown dwarf can sustain deuterium fusion for a few million years. During this time, it glows with a dim, reddish or purplish light, something like a very cool, very faint star. But the deuterium runs out, and when it does, the brown dwarf begins to cool. Slowly, over billions of years, it fades. It contracts slightly, stops glowing, grows colder and dimmer. It does not explode. It does not die in any dramatic sense. It simply fades like an ember losing its heat until it is effectively invisible. A cold, dense sphere of gas drifting silently through the dark, too small to be a star, too large to be a planet. The galaxy is thought to be full of brown dwarfs, hundreds of billions of them, perhaps. Cold, dark, failed stars moving silently through the Milky Way, invisible to most telescopes, detected only when we specifically look for them in the infrared, or when they pass close enough to a background star to bend its light gravitationally in what we call a microlensing event. They are the quiet majority, the ones that almost made it, and there is something tender in the dark of a late night in thinking about them. Cold worlds, not quite stars, not quite planets, drifting through the galaxy in their billions, unseen and uncounted. The cycle of star formation is not self-sustaining in isolation. It needs input. It needs events, disturbances, triggers that compress the gas enough to push it past the gene's threshold and set the collapse in motion. One of the most powerful of these triggers is the death of a massive star. When a massive star, a star many times the mass of our sun, reaches the end of its life, it explodes in a supernova. In the space of a few seconds, the core of the star collapses, and the resulting explosion releases more energy than our sun will emit in its entire 10 billion year lifetime. A supernova can briefly outshine an entire galaxy. The shock wave from a supernova travels outward through the interstellar medium at hundreds or thousands of kilometers per second. When it reaches a nearby molecular cloud, it slams into the cloud's edge like a hammer blow, compressing the gas it encounters to densities far above the gene's threshold. That compression can trigger almost instantaneous star formation, at least instantaneous in cosmic terms, meaning within a few million years. It is thought that the birth of our own sun may have been triggered, or at least accelerated, by exactly such a supernova shock wave. There is isotopic evidence in meteorites, ancient rocks that formed in the earliest days of the solar system and have preserved a chemical record of that time, suggesting that a nearby supernova injected short-lived radioactive isotopes into the solar nebula just before or during the sun's formation. Those isotopes could only have been produced in a supernova explosion that happened within, at most, a few million years of the solar nebula's formation. If this is correct, then our sun owes its existence, at least in part, to the death of another star. A star that lived and burned and exploded before our solar system existed. A star we will never know in a location we can no longer determine, that died so that we might eventually be born. Every birth, even at the cosmic scale, involves sacrifice. The death of the old creating the conditions for the new. The cycle is ancient. It will continue long after our sun has completed its own life and returned its material to the interstellar medium for the next generation of clouds and stars. In the Milky Way today, roughly 2 to 3 new stars form every year. Not every year produces exactly the same number, and the rate has varied over the galaxy's lifetime. It was much higher when the galaxy was young and its molecular clouds were richer and denser and more numerous. But today, the Milky Way is a middle-aged galaxy. Its star formation rate has declined from the frantic pace of its youth. New stars are still forming in the Orion Molecular Cloud, in the Carina Nebula, in the star-forming regions of the Sagittarius Arm, but at a gentle, sustainable pace. And as you lie here in the dark, somewhere in the galaxy, a star is being born. Not this second, the process is too slow and too spread out for that. But within this year, within this decade, somewhere in the dark heart of a molecular cloud, a prestellar core has just crossed the gene's threshold, or a protostar has just emerged from its second collapse, or a T-Tauri star, after millions of years of contraction and flaring, has just quietly, invisibly, lit the first nuclear fire in its core and stepped onto the main sequence. A star has just been born, and no one, no astronomer, no telescope, no spacecraft has witnessed it. The moment itself was hidden, as all such moments are, inside a cocoon of dust and gas and time. We will piece it together afterward, from the evidence it leaves behind. We will see the Herbig-Haro objects, the infrared glow, the bipolar outflows. We will reconstruct the birth from the clues, as we always do with things we cannot directly witness. We are, as a species, very good at reconstructing the past from clues. We do it in our sciences and in our lives. We look at the fossil record and rebuild the history of life. We look at the sediment layers in a rock and read the history of a sea. We look at the light from distant galaxies and reconstruct the history of the universe. We piece together, from fragments and signals and mathematical reasoning, the story of things that happened before we were there to see them. And in doing so, we participate in those stories. We become part of them. The story of the birth of a star is not just a story about gas and gravity and nuclear physics. It is a story about us, because we are the universe's way of telling it to itself. There is a concept in physics called detailed balance. It describes a system in which the rate of one process exactly equals the rate of the reverse process. Not because nothing is happening, but because the forward and reverse rates are precisely matched, creating a dynamic equilibrium. Water evaporating from the surface of a lake and condensing back into it. Molecules being ionized by radiation and recombining in the dark. Star formation and stellar death are not in detailed balance. Stars form and die, but the material is not simply recycled unchanged. Each cycle of stellar birth and death takes some material out of the gas phase permanently, locked into compact objects like white dwarfs, neutron stars, and black holes, and adds slightly more heavy elements to the gas that remains. Over billions of years, the interstellar medium gets progressively richer in heavy elements and progressively poorer in the pristine hydrogen and helium that dominated the early universe. Eventually, many billions of years from now, the Milky Way will exhaust its star-forming gas. The molecular clouds will be gone, consumed, or dispersed. The rate of star formation will fall to zero. The oldest stars still burning will be the small, cool, red dwarf stars, which consume their hydrogen so slowly that they can persist for trillions of years. The more massive stars will long since have lived and died. The sun will have swelled into a red giant, swallowed the inner planets, and collapsed into a white dwarf, slowly cooling into a black dwarf over hundreds of billions of years. The galaxy of the far future will be quieter, darker, dominated by cooling embers and the long, slow orbits of cold stellar remnants around a supermassive black hole. No new lights will switch on. The era of star formation will be over, but that is so unimaginably far from now. Trillions of years from now, the universe itself is not yet 14 billion years old. We are still in the early, active star-forming phase. We live in a privileged era, a golden age of stars, when the Milky Way is still rich with molecular clouds, still building new suns, still illuminated by the ongoing work of creation. If intelligent beings exist somewhere in that distant future, beings perhaps so different from us that we would not recognize them as life, they will look back at our era the way we look back at the very early universe, as a time of extraordinary activity, of richness and change, before things settled into a long, cold quietude. We do not realize how fortunate we are, in a cosmic sense, to exist when we do, to live in the era of star formation, to be able to look up at a sky full of active, burning suns and know that more are being born, right now, in the dark corners of the galaxy. We will never see a star form from beginning to end, not with our own eyes, not in a single human lifetime, not in all of recorded human history. The process is simply too slow, stretched across timescales that dwarf not just individual lives but entire civilizations. And yet we understand it. We have pieced it together from observations of many different stars caught at different points in the process, like reconstructing the life cycle of a tree by looking at seeds, saplings, mature oaks, and fallen logs all at once, and reasoning about the progression from one to the next. We observe prestellar cores with radio telescopes. We detect embedded protostars with infrared observatories. We photograph Herbig-Haro objects with visible light telescopes. We measure the rotation curves of protoplanetary disks with interferometers. We watch T Tauri stars flare and calm. We measure the chemical composition of the gas and dust in molecular clouds. And from all of this, from hundreds of different observations of hundreds of different objects at hundreds of different stages, we have assembled a picture that is, while still incomplete in its details, coherent and beautiful, and almost certainly right in its broad strokes. Science is, in a sense, the art of reconstructing what cannot be directly witnessed. And the story of stellar birth is one of its great achievements. Let me tell you about dust. We have mentioned it several times in passing tonight: the dust in molecular clouds, the dust in the protostellar cocoon, the dust that blocks visible light and scatters infrared light and threads through the disks of forming planetary systems. But dust deserves a moment of its own, because it is one of the unsung heroes of star formation and of life itself. The dust grains in a molecular cloud are tiny. Most of them are smaller than a micrometer, smaller than a bacterium. They are made of silicates and carbon compounds and ices: water ice, carbon monoxide ice, ammonia ice, coating the silicate and carbon cores in thick, cold mantles. They are, in a sense, the mineral grains of space. And they are everywhere in the interstellar medium. These tiny grains are what make molecular clouds dark to visible light. Each grain absorbs and scatters the starlight trying to pass through the cloud, building up to a cumulative opacity that can block millions of stars behind a single dense cloud. The Great Dark Nebulae, the Horsehead Nebula, the Coalsack, the dark lanes of the Milky Way are all dense concentrations of this interstellar dust. But dust is not just an absorber of light. It is a catalyst of chemistry. The surfaces of dust grains are places where atoms and molecules can meet and react, catalyzed by the grain surface in ways that would be essentially impossible in the free gas phase. The formation of molecular hydrogen itself, the most abundant molecule in the universe, happens primarily on dust grain surfaces. An individual hydrogen atom lands on a grain, sticks, and waits. Eventually, another hydrogen atom lands nearby. They find each other, bond together, and depart as a hydrogen molecule. Without dust, molecular clouds could not form and hold their molecular hydrogen. Without molecular hydrogen, the coolant molecules needed to radiate away the heat of collapse, carbon monoxide being the most important, could not exist in the necessary concentrations. Without those coolant molecules, the clouds could not get cold enough to form stars. Dust makes stars possible, and therefore, dust makes planets possible, and therefore, dust makes us possible. There is no single event in the history of the universe that led to us. There is a chain of events, each dependent on the last, stretching back to the Big Bang. The formation of hydrogen in the first seconds of the universe. The cooling that allowed hydrogen to become neutral atoms 380,000 years later. The slow gravitational gathering of hydrogen into the first molecular clouds over hundreds of millions of years. The formation of the first massive stars and their quick, violent deaths, seeding the interstellar medium with the first traces of carbon and oxygen and silicon and iron. The condensation of those atoms onto the surfaces of interstellar dust grains, enabling the chemistry that would make all subsequent molecular clouds richer and more chemically complex. Generation after generation of star formation and death, each one adding to the richness of the mix. And then, about 4.5 billion years ago, in an unremarkable corner of the Milky Way, a slightly denser than average region of a molecular cloud crossed the Jeans threshold. Perhaps aided by a nearby supernova shock, perhaps not. And from that crossing eventually came a protostar and a disk and a young sun and planets, and one particular planet at just the right distance from the sun, with just the right chemistry, with liquid water pooling in its basins. And 3.5 billion years after that, on a Saturday morning or a quiet Tuesday evening, or whenever you first looked up at the night sky and felt something wordless and large, that is what you were feeling. The pull of recognition. The universe recognizing itself through the particular instrument of your consciousness. We return, in the end, to where we began. to the darkness between the stars. It does not feel like a beginning place, the dark. Feels like nothing, like absence, like the space between thoughts, the pause between breaths, the moment between falling asleep and being asleep. But we know now that it is not nothing. We know that the dark between the stars is threaded with gas and dust, with magnetic fields and turbulent motions, with the faint cold glow of molecules bonded on the surfaces of grains no wider than a bacterium. We know that in the darkest, coldest, most isolated places in the galaxy, the slow work of star formation is going on, has been going on for billions of years, will go on for billions more. The darkness is not empty. The darkness is pregnant. The darkness is what comes before. There is a small comfort in that, I think, on a night like this. We are not lying in darkness waiting for nothing. We are lying in darkness that is full of potential, full of patient processes, full of the slow, certain work of gravity and time. The darkness is doing something, even now, even here, even in the quiet of a room where someone is trying to fall asleep. The world goes on. The stars burn. The molecular clouds drift and thicken. The prestellar cores collapse. And you can let all of that happen without you, just for now. The universe does not need your help tonight. It has been doing this for 13.5 billion years, and it is quite good at it. The T Tauri stars we observe today, those young, wild, variable suns in their protoplanetary disks, are in some ways the closest thing we have to a portrait of our own young sun. Before the planets had fully formed, before the oceans filled, before the first molecules of self-replicating chemistry folded themselves together in warm pools and tidal shallows. The T Tauri phase of the sun was the universe's preparation for everything that came afterward. What was the early solar system like in those first millions of years? The sun was larger than it is today, still contracting toward its final size. It was brighter in some wavelengths, particularly ultraviolet and X-ray, and it was variable, flaring regularly, blasting the inner solar system with energetic particles. The disk around it was a swirling sea of gas and dust, with small rocky bodies, planetesimals, already beginning to form and collide and grow. The inner solar system was violent. Planetesimals crashed into each other at tremendous speeds. Larger bodies grew at the expense of smaller ones in a process called accretion, essentially the same process by which the protostar itself grew from the infalling envelope, just on a smaller scale and at slower speeds. The largest growing bodies began to differentiate. Their iron sank to the center under gravity, while lighter silicate materials floated to the surface, creating the layered structure, core, mantle, crust that we see in Earth today. And all of this was happening while the sun itself was still settling into its final form, while the T Tauri winds were sweeping the uncaptured gas out of the inner solar system, while the giant planets, Jupiter and Saturn and Uranus and Neptune, were forming in the outer disk, their immense gravity sculpting the architecture of the whole solar system. The story of Earth's formation and the story of the sun's formation are not separate stories. They are the same story happening in the same place at the same time from the same original molecular cloud core. The sun and its planets are siblings. They were born together. They share the same origin. And so, in a sense, do we. Let me take you somewhere quiet now. Somewhere far from any star, far from any galaxy even, far out into the intergalactic void, where the density of matter is lower than anything we can reproduce in any laboratory on Earth, where there is perhaps one hydrogen atom per cubic meter of space, where the temperature is only a few Kelvin above absolute zero. In this place, if you could somehow be in this place, which you cannot, for several entirely insurmountable reasons, the silence would be profound. There would be no sound, of course. Sound requires matter to vibrate, and there is almost no matter here. There would be no light from any nearby source. The galaxies would be visible in every direction. smeared across the sky like faint clouds, each one containing hundreds of billions of stars, but all of them so far away that their combined light would be dimmer than a candle seen from miles away. You would be in a true desert, empty in a way that Earth is not and has never been and will never be. And yet, even here, even in this most desolate corner of the universe, there is hydrogen, scattered, thin, barely there, but present. And given enough time, billions of years, even this sparse gas can be slowly gathered by gravity, slowly concentrated, slowly drawn into the filaments of the cosmic web that connects galaxies. Slowly, imperceptibly, over eons, it could end up in a galaxy, in a molecular cloud, in a prestellar core, in a protostar, in a star. Even the voids are not permanent. Even emptiness, given enough time, is only temporary. The universe is patient. It does not rush. It does not need to. It has all the time there is. And that patience, that cosmic, unhurried 13 billion year patience, is one of the most calming things I know about the universe. Not everything needs to happen now. Not everything needs to be done tonight. Some things take millions of years. Some things take longer. And they are not less real, not less meaningful, not less beautiful for taking so long. In fact, the slowness is part of the beauty. A star that formed in 10 minutes would not be the same as a star that formed over 10 million years. The long gestation, the slow work of turbulence and magnetic fields and ambipolar diffusion, the patient accumulation of mass in the protostar, the long T-Towery youth, all of that slow process shapes the final object. It determines the star's rotation rate, its chemical composition, the structure of the disk that will become its planetary system. The slowness is not a delay on the way to the real thing. The slowness is the real thing. We are impatient creatures as a species. We like things to happen quickly. We have built technologies that make things happen faster and faster. Information travels at the speed of light. Goods arrive in hours. Communication is instant across any distance. We have optimized for speed in almost every domain of human life. And there is much that is wonderful about that. The speed of science, the speed of medicine, the speed of communication, these are genuine goods. But there is also something we lose in our impatience. A relationship with the slow, with the patient, with the things that take as long as they take. A molecular cloud teaches, if we are willing to listen, that the most important things do not happen quickly. That the things worth waiting for are worth waiting millions of years for. That there is dignity in slowness. That there is beauty in the long, patient work of becoming. Your body, right now, lying in the dark, is the product of that long, patient work. Every atom in you has been on a journey of billions of years. From the Big Bang to the inside of a stellar core. From a supernova to the interstellar medium. From a molecular cloud to a protoplanetary disk to a young Earth to the ocean to the first cells to the first multicellular organisms to the first vertebrates to the first mammals to the first primates to your ancestors to you. You are the latest and most improbable chapter in a story that began 13.8 billion years ago. You are, in the most literal and physical sense, stardust that has woken up. Stardust that has learned to ask questions. Stardust that lies in the dark sometimes and wonders about the darkness. And that wondering is perhaps the most extraordinary thing that has happened in the entire history of the universe. More extraordinary than the birth of the first star. More extraordinary than the formation of galaxies. More extraordinary than the explosion of a supernova scattering its heavy elements into the void. Because the universe has always had stars. It has had galaxies for 12 billion years. It has had atoms for almost as long. But for most of its history, the universe had no way of knowing itself. No way of being curious about itself. No way of marveling at its own complexity. And then, perhaps 3 or 4 billion years ago, something began. something small and uncertain and tentative. Chemistry in warm water somewhere on a young planet. Chemistry that began to copy itself. And over billions of years, patiently, slowly, in the way the universe does everything, that chemistry became life. And life became complex. And complex life became conscious. And consciousness became curious. And a curious, conscious creature looked up at the night sky and said, "I wonder what those are." That question, that first wondering, was the universe looking at itself. For the first time in its entire history, looking at itself and saying, "What am I?" We are still asking that question. And the asking is sacred in its own secular way. The asking is why we are here. The asking is what makes the universe meaningful. There are about 200 billion stars in the Milky Way. Estimates vary, but the number is somewhere in that range. 200 billion suns, each one the product of the same process we have followed tonight. Each one with its own molecular cloud origin, its own prestellar core, its own protostellar phase, its own T-Tower youth. Each one carrying in its interior the record of all the generations of stars that came before it. The chemical legacy of stellar births and deaths stretching back to the first stars that formed when the universe was young and new. And each one is currently burning, right now, at this moment, in the quiet dark of a night you are lying in. Each one fusing hydrogen into helium, releasing the energy that keeps the universe bright, that heats the planets orbiting around them, that powers the chemistry of life on any planet fortunate enough to be in the right zone at the right distance with the right conditions. The Milky Way is alive, not in the biological sense, not with cells and metabolism and reproduction, though it contains all of those things, distributed among its billions of worlds, but alive in the sense of ongoing, active, continuous process. The galaxy is not static. It is forming stars and dying stars, building heavy elements and distributing them, gathering gas and dispersing it, forming clouds and dispersing them, having its spiral arms compressed by density waves that roll through the disk like ripples in a slow pond. The galaxy is doing something. It has always been doing something, and it will continue doing something slower, quieter, but still active for billions of years to come. We are inside that process. We are part of that process. The atoms in your body are between stellar lifetimes right now. They were forged in a star, scattered in a supernova or stellar wind, gathered into a molecular cloud, incorporated into a new solar system, assembled into a planet, stirred into the chemistry of life, and eventually, improbably, miraculously, arranged into you. And after you, after all of us, those atoms will continue. They will return to the soil, to the air, to the water. Some of them will be lifted into the atmosphere and eventually escape to space. Some will be locked in rock for billions of years. And eventually, in 5 billion years or so, when the sun swells into a red giant and the inner planets are engulfed, those atoms will be scattered back into the interstellar medium, enriched with the products of another stellar lifetime, ready to be gathered into the next generation of clouds and stars and planets and perhaps, who knows, the next generation of curious, wondering beings who look up at the night sky and ask, "What are those?" The cycle goes on. The cycle will always go on. And there is something in that, something in the permanence of the cycle, even amid the impermanence of individual lives and individual stars, that I find genuinely comforting. The specific arrangements of atoms that constitute you or me or any living thing are temporary. All temporary. Everything that exists will eventually be disassembled and reassembled into something else. Nothing is permanent at the level of individual objects, but the process is permanent. The cycle is permanent. Matter will always be drawn together by gravity. Clouds will always form. Stars will always be born. And wherever there is a star with a planet at the right distance and time and liquid water and the chemistry that self-replicates, wherever those conditions are met, the universe will try again. We'll try to make something that wonders. We'll try to make something that looks up. We may not be the only ones doing the looking, and that is a thought worth holding quietly for a moment. There are, by the best estimates of modern astronomy, somewhere between 10 billion trillion and 1 septillion stars in the observable universe. A septillion is a 1 followed by 24 zeros. 10 billion trillion is a 10 followed by 22 zeros. Even the lower end of those estimates represents a number so large as to be effectively impossible to comprehend. And around many of those stars, perhaps most of them, based on the exoplanet surveys of the last few decades, there are planets. The Kepler Space Telescope and its successors have taught us that planets are not rare. They are common. The default state of a young star with a protoplanetary disk is to produce planets. Our solar system's 8 planets are not an aberration. They are a typical outcome. Of those planets, some fraction will be at the right distance from their star. Some fraction of those will have the right chemistry. Some fraction of those will have liquid water. Some fraction of those will develop chemistry. Some fraction of those will develop self-replicating chemistry. Some fraction of those will develop life. And some fraction, we do not know how small a fraction, of those will develop life that eventually, over billions of years, becomes curious enough to look up. We may be alone. The universe is large enough, and life's origin uncertain enough, that we cannot rule it out. Perhaps the emergence of consciousness required a chain of events so improbable that it happened only once. Perhaps we are the only curious atoms in the observable universe. But we may not be. And that possibility that somewhere around another young star born from another molecular cloud, on another planet with another ocean, there are other curious beings looking up at their own night sky, asking their own version of our question. That possibility is one of the most extraordinary things the human mind has ever contemplated. And it is real, not as fantasy, not as wishful thinking, but as a genuine, scientifically plausible possibility that follows from everything we know about star formation and planet formation and the origin of life. We may not be alone in the universe's wondering. And on a quiet night, lying in the dark, that thought can feel either enormously lonely or enormously warm, depending on how you hold it. I prefer to hold it warmly. We have been talking for a while now, and the story we have followed, from a thickening in a cold molecular cloud to the moment of nuclear ignition, from a prestellar core to a main sequence star, is one of the longest stories in nature. One of the most patient, one of the most quiet, and it is a story without an audience for most of its length. The collapse of a prestellar core happens in complete darkness, with no light escaping the dusty cocoon. The protostar forms and grows in silence, its birth recorded only in the faint signatures of infrared radiation detectable only with telescopes we built very recently in the history of science. The T-Towery phase unfolds over millions of years, longer than any civilization, longer than our entire species. No one is there to watch. No one is there to witness. The star is born alone, in the dark, in silence. And then, one day, millions of years into the process, the cocoon clears, the disk settles, the nuclear fires ignite, the star shines, and it shines into space in all directions for billions of years. Eventually, the light from that star reaches a small blue planet in an ordinary solar system in the outer regions of a spiral galaxy. And on that planet, on a clear night, a creature lying in the dark opens its eyes and sees a point of light in the sky that was not there before. Or an astronomer, scanning the sky with a telescope, catalogs a new star. Or a child points up and asks, "What is that?" The star has been waiting patiently for billions of years, and now finally it has been seen. That is not nothing. That is the universe completing a circuit. The star, born in darkness and silence, finally seen by the curious eyes of the matter it helped to make possible. The dust that became the sun that seeded the interstellar medium that became another cloud that became our sun that became Earth that became us. The same matters also, in a very specific and literal sense, true. The atoms in the neurons firing as you listen to these words were forged in stellar cores. The electrical signals traveling through your brain right now are running on chemistry made possible by elements produced in supernovae. Your consciousness, whatever that extraordinary, poorly understood thing is built from the matter the universe produced in its star-forming regions, shaped by billions of years of evolution, and is now engaged in the act of understanding the very processes that made its existence possible. The universe, through you, is understanding star formation tonight. How remarkable that is. How quietly remarkable. Let the star go on shining. Let the molecular cloud go on drifting. Let the prestellar cores go on collapsing in their dark, patient way. None of it needs your attention tonight. None of it needs your help. The universe has been doing this far longer than you have been here, and it will continue long after. You can simply rest now. You can let the story go on without you for a little while. You can set down the thinking and the wondering and the gentle awe that has been carrying you through this night, and let your body be what it is. A brief, remarkable, improbable arrangement of atoms, lying in the dark, growing still. The stars are still out there, even behind the roof above you, even behind the clouds, if there are clouds tonight. They are always there, burning steadily, patient, unhurried, doing the long, slow work they have always done. And somewhere, in the dark heart of a molecular cloud somewhere in the Milky Way, a prestellar core is crossing the gene's threshold, tipping over the edge, beginning its long, slow fall towards starhood. It will take millions of years. It does not need to be hurried. Neither do you. Tonight, we followed the longest birth in nature. We began in the cold dark of a molecular cloud, that vast, almost invisible reservoir of gas and dust floating between the stars. We watched gravity begin its patient work, pulling matter slowly together over millions of years. We learned about the forces that resist the collapse, the turbulence that stirs the cloud like slow weather, the magnetic fields that thread through it like an invisible skeleton, the thermal energy that pushes outward against every inward pull. We followed a prestellar core as it crossed the gene's threshold and began its irreversible collapse. We watched a protostar emerge from the second collapse, hidden in its dark cocoon, blasting jets into the surrounding cloud, feeding hungrily from its accretion disk. We saw the cocoon clear. We met the T-Tauri star, young, wild, flaring, surrounded by the swirling disk that would become a planetary system. And we arrived, finally, at the moment of true stellar birth, the quiet, invisible ignition of nuclear fusion in the core, and the settling of a new star onto the main sequence, where it will burn steadily for billions of years. We also remembered, along the way, that we are part of this story, that the atoms in our bodies were forged in stars that died before our sun was born, that we are stardust that has learned to wonder, that the story of star formation is, at some deep level, our own origin story, told in the language of physics and time. You do not need to hold all of that tonight. You do not need to carry any of it. You do not need to understand every part or remember every step. The universe will keep forming stars whether you remember the gene's instability or not. It will keep cycling matter through clouds and protostars and planetary systems, patient and unhurried, for billions of years to come. You can simply let the questions drift. Let the molecular clouds go on drifting. Let the stars go on shining. Let the gravity go on pulling, slowly, gently, inevitably. Let your breath grow slow and even. Let your thoughts begin to loosen and grow soft at the edges, like the outer layers of a molecular cloud thinning in the wind of a nearby star. Let the day go. It will still be there in the morning, rearranged and manageable and lit by the steady light of a 4.5 billion-year-old star. If you enjoyed this journey tonight, we would love it if you subscribed to the channel or left a comment letting us know where in the world you are listening from. It means more than you know to hear that someone somewhere drifted off to still here, still awake, still quietly curious, there is another video waiting. Another corner of the universe to explore. Another long, patient story told at the pace of the cosmos, at the pace of a late night, at the pace of someone lying in the dark who just wants to understand a little more about the extraordinary place they find themselves in. But for now, let yourself be still. The prestellar cores are collapsing. The protostars are growing. The T-Tauri stars are flaring in their youth. Out there in the dark, millions of light years away. And you are here, warm, safe, small in the best possible way. A brief arrangement of stardust on a pale blue planet, resting in the dark, under the light of a star that was once a cloud, that was once almost nothing. Let that almost nothing hold you now. Let the darkness be kind. Sleep well and good night.